So till now in this module, we have looked at classification and regression, both of them. Now let's look at metrics. Mostly we'll look at classification metrics in this video. So measurement is the most important thing in data science because even if you are improving your model, how will you know that you are improving? So we need measurement and metrics are the way to do measurement in a way, right? And what we really care about. So there could be business metrics and there could be general ML metrics, right? Examples of business metrics are click-through rate, revenue, profits, number of new users, which business really cares about. Generic ML metrics examples could be like accuracy, precision, recall, and you'll see the definition of these soon enough. Now, the thing is, there are various kinds of metrics. Not all errors are equal. Not all performance metrics are equal. They have their own pros and cons. And that's why we need to be aware of various kinds of metrics. And metrics helps capture business goal into a quantitative target, which we can measure and track and improve on. Usually, even generic ML metrics or even business metrics are hard to optimize directly. And one way to do it is via loss function. So in some sense, loss function is a proxy which we try to optimize. But we truly want is to improve either a generic ML metric or a business metric. That's what we care about. But loss is just a proxy which we can optimize on. And generally, we want to improve the metric on the validation set or dev set. It kind of is helpful to track performance over time or even compare two instances of model. So, for example, maybe let's say you chose some metric like accuracy or something, and you compute that accuracy. So let's say you are building a new model every day on some past data, some sliding window data. Let's say 7 days data you compute the metric on 8 day, and you do this in a sliding window kind of fashion for every day. So you kind of get like a trajectory of accuracy. And let's say you're training the model every day. Maybe someday the accuracy dropped suddenly. And it could be because of various reasons, including this being some issue in the training data, which kind of comes from some flaw in engineering systems. So metrics are useful even to track the performance over time. And these kind of issues shows up if there's some issue in the system or some shift in the data behavior or something like that, right? So it kind of helps us to track performance over time. Or let's say if I build a model number one or model number two and so on, right? So metric help us decide which model is the best, right? And it's also useful for debugging. Maybe when we discuss case study later on, I'll show you how metrics can be used for debugging. But yeah, I mean, this was one example, right, of debugging that suddenly your metric dropped and all. So you train your model every day, but you decide on a certain criteria whether you want to use a new model or you continue to use the old model, right? So anyways, like these are like the high level things why we need metrics. Mostly there are like three major categories of metrics in terms of ML metrics. One is classification metrics, one is regression metrics, and one is information retrieval or ranking metrics. These are like the three major categories. Of course, there could be more, but these are the main ones. So in this video, we'll discuss mostly about classification metrics, and I'll just give you a setup. So we have data points xi, comma yi, and yi could be either a 0 or a 1. 1 is a positive class, and 0 is a negative class. Okay. And we kind of build a model P of y given x, where if you give it the input data in terms of feature vectors x, it kind of gives you a probability for a class. Let's say y equal to 1 or something, right? And this probability will be a score between 0 and 1. So if I draw it to the scale, this is 0, this is 1, and you get some value between this. And what happens is we kind of choose some kind of threshold tau. Let's say tau equal to 0.5 or something. And we say that any probability above 0.5 I'll classify it as class number 1 or positive class. Anything below this threshold tau will be classified as negative class. So that's the setup. And once you are able to classify these things, you should be able to compute various metrics, which we will discuss soon enough. Before we get started, I wanted to discuss confusion matrix, and it's not that difficult. So you have a scale between 0 and 1. You get a sample x, you feed it into your probability model P of y given x, and you get some score which will fall in between this 0 and 1. And you have a threshold tau. So if your probability is above this threshold, you have a positive class prediction. And if it's below threshold, you have a negative class prediction. So what I'm saying here is y hat of tau is your prediction. It can be either a 0 or a 1 based on whether the probability is falling in this area or this area. Okay. So anyway, so that's my y hat, which is my prediction. It's either 0 or 1, which is this estimate thing, right? Either it's a 0 or a 1. Then I have my truth, which is my y, which could also be again a 0 or a 1. Now there are these things like false positives, FP, true positive, TP, false negative, FN, and true negative, TN. Just take an example of FP. I clean it up a bit. So on estimate side, we have y hat. On the truth side, we have y. Let's consider this metric FP, which is false positives. So false positive is just the total number of items which satisfy this condition that the truth was negative class, but my prediction is positive class, right? So it is a kind of a false positive, but truly it was negative. So that's my definition of false positive. Similarly, you can see this grid, 2 cross 2 grid, and just by looking at the grid, you can find what is the meaning of each. For example, for true positive, your estimate y hat should be 1, and the truth also should be 1. So my true positive is total number of samples where my truth and estimates both are positive class. Similarly, I have true negative. That's a situation when my estimate is also negative class and my truth is also negative class. And then I have false negative, where my estimate is a negative class, but my truth is a positive class. So that's the definition of true negative, false negative, and true positive. Now these sums, right? So this n is actually total number of negative class samples, and p is my total number of positive class samples. P hat here is the total number of positive class predictions, not the truth. Similarly, n hat is my total number of negative class predictions. So this is all the components of my confusion matrix. I hope this is clear. Okay. Now, next thing is confusion matrix we have seen. Now we want to look at two metrics, which is accuracy and prevalence. So let's look at accuracy first. Okay, let's start with prevalence because actually prevalence is not a function of model. It's the function of data set. And prevalence is simple. It's kind of class Q in the data set. So prevalence is just equal to P divided by P plus N, which is basically total number of positive samples, which are the positive truth samples, divided by total samples. That's prevalence. It kind of tells me the skew in the data in terms of what is the percentage of positive samples with respect to total samples. That's prevalence. Next is accuracy. And that is also simple. It's just total number of correct sample divided by total samples. And that will be equal to total number of correct sample is, now if you focus on TP and TN, true negative is what? Estimate is also 0 or negative class, and truth is also negative class. So true negative is actually the ones which are correctly classified. Similarly, true positive is also something which is correctly classified, divided by total number of samples, which is P plus N. So that's my accuracy. And one drawback of accuracy is that it's extremely sensitive to prevalence, in a sense that, let's say, I'm kind of predicting cancer situations, cancer, and let's say only 0.1% people have cancer. or even more extreme, right? 0.01%. So 99.99% people don't have cancer. So I could have a very dumb rule, which is predict that you don't have cancer all the time. Then my accuracy will be what? 99.99%. So you will think that your accuracy is 99.99%, but in a true sense, your rule is truly dumb. You're just saying that no one has cancer. But is that a good model? No. So that's also a drawback of accuracy, but accuracy is useful in many situations when you don't have this kind of extreme skew. But if you have this kind of extreme skew, then accuracy is not a great metric. Okay. So next two metrics I wanted to discuss was precision and recall. But to discuss that, what I want to share first is this example of search engine. So let's take two situations. One is like you're a normal web surfer like me and you, where we go to Google and search for things every day. And if you're a web surfer, what you really care about is that the relevant results are in the first page. But let's say if you're a paralegal, then you might be fine with a lot of mistakes in the first page, but you don't want to miss any cases in the first 5 pages, let's say. You really want to like explore exhaustively, and you don't want to miss any cases which is relevant to your query. So that's another situation, right? And these two use cases are kind of different in a sense that the web surfer case is saying that my precision should be high, right? And the definition of precision is simple. You take true positives, which is just saying that I take all the counts where my true positive class is classified correctly. So I take the true positives and I will divide that will with true positive plus false positive, right? So this is also equal to TP by P hat. So precision means that from all the positive predictions, which is P hat, how many of them were correct? That's precision. The paralegal situation is a system where I am really wanting a high recall system. And the definition of recall is also simple. It's true positive by true positive plus false negative, true positive plus false negative. So this can also be written as true positive by P. Again, recall is about I take all the ground truth data which is positive class and see how many of them has been classified correctly. That's my recall. And if you think about it, that's exactly what you want from the paralegal situation. You have lots of documents and you take all the documents which has a positive class label as truth. So let's say these many. And out of these few of them which were relevant, what proportion of them you captured is the recall, right? And that's what you want from the paralegal situation. But in terms of web surfer, you want is you make like 10 prediction and how many of them were correct. That's what you want from a web surfer, and that's the high precision system. So this was in terms of TP, FP, and all those stuff. But there's another way to look at it, which is I think I have it in my next page. Okay, I have it in my next page. Again, my estimate y hat could be either 0 or 1, and my true label yn can also be 0 or 1. So precision is simple, which is I take all the samples where my labels are matching, but in a sense that I ignore the zero ones. For example, 0 into 0 is 0, right? So multiplication of yn and yn hat is just basically counting my true positive because it will be a 1 only when both of them are positive. That it should be a positive class and it should also match positive prediction divided by y hat sum, which is just again p hat, right? And similarly here also the denominator is p and the top is tp. So this is another way to write the same thing, again precision and recall. And based on different situation, we might expect different precision recall expectations. But at the least, we should know that either we need a high recall system or the high precision system because that's kind of like a design choice, right? Okay. Now, the interesting thing about confusion matrix is that if you normalize this confusion matrix per row, then you get certain kind of matrix. For example, I have this 2 cross 2 thing, right? Tn, Fp, Fn, Atp. And if I divide this matrix by the row sum, which is n and p, you'll get something like this new table, where first thing was Tn by n, the second one was Fp by n, because I divided the first row by n. Then the second row I divide by p, so I get Fn by p, Tp by p. And based on this kind of normalization, I get certain metrics. The most important ones here are, actually here everything is important. Uh, so Tn by n. But by the way, if you normalize it by row sum, which we have done in this slide, you'll all of them are rates. For example, this Tn by n is called true negative rate. Fp by n is called false positive rate. Fn by p is called false negative rate. Tp by p is called true positive rate. And true positive rate also has another name called recall, which we just discussed in the previous slide. So there could be various situations when you need different things, but yeah, it depends on the use case. We have already discussed when we want a high recall. A false positive rate is a situation where okay, let's say you're doing robot detection or something, and then you have this robotic and human labels, right? And here false positive rate is the percentage of humans which you fail to capture through your model. Okay, so that's false positive rate. So anyways, it depends, but yeah, you need to know these definitions, but usually based on the application, it just falls in place. These are just the names of these things. And false positive rate is also called type 1 error, and false negative rate is also called type 2 error. And yeah, I mean, these are just names. You don't need to worry too much about it. But true negative rate, false negative rate, false positive rate, true positive rate. You need to know the meaning of these. These could also be part of discussions in the interview, so it's actually important. Then it also has other names. For example, true negative rate is also called specificity. True positive rate is also called sensitivity, and type 1 error, type 2 error, and things like that, right? So at the least, you should know the names of the rates and what they mean in terms of formula. And one interesting thing about rates here in this slide is the denominator is always from the ground truth. It's not n hat or p hat, it's n or p, right? So that's the interesting part which might help you remember. For example, if you are looking at true positive rate or true negative rate, it is just Tp by p or Tn by n. Simple. False positive rate is actually number of false positive and the rate of it. But if it's a false positive, then truly that sample was a negative sample. So if you take a rate out of it, it will be Fp by n and Fn by p. So that's kind of a way to remember it. It's not necessary to remember, but try to. Okay. Now, if you normalize the same thing by column, then you get these things, which is Tn by n hat, Fn by n hat, Fp by p hat, and Tp by p hat. And Tp by p hat is the one which is the most common one in this table. It's the meaning of precision. And then there are other things like FDR, which is false discovery rate, FDR, and FOR is false omission rate. Anyways, like precision is the most important one, and the second most important one I feel might be false discovery rate. So yeah, so that's how normalization by column can give you newer metrics, and they also might be useful in various cases. But in my experience, precision is the most important. FDR might be useful in some cases, but still not that popular. But anyways, I'm just saying that the situation will kind of tell you what you need, and it just has a name for it. So it's just a nomenclature thing. But usually you know what you want to compute or what ratios are important to you. Okay. So usually your probability score will be between 0 and 1. And then you will have some threshold T or tau. And based on that threshold, you will have a classification of positive class or negative class. And based on that classification and the ground truth, you could find your true positive rate and false positive rate. And for different tau, you'll get different TPR and FPR, right? So if I keep changing my tau from 0 up to 1, I'll get a kind of a list of TPR and FPR as shown in a curve of any color, let's say the blue color curve. So you'll get like a trajectory of TPR FPR pairs as you change your threshold, right? Now, let's say if I wanted to compare two models, which is model A and model B, but maybe I don't want to choose a threshold. I just want to know how well are the samples ranked so that the positive samples are ranked above the negative samples. Let's say that's my goal, kind of, right? So if you want to do that, you can plot these trajectories of TPR comma FPR and you get these two curves for model A and model B, right? Now the question arises which one of them is a better model. So there's something called area under the ROC curve. I think it's the second. Oh, okay, it's not there. But yeah, basically you find the area under the two curves and the curve under which you have a higher area is the better model. For example, in this case, model A or red curve is better because it has higher area under the curve. Okay, we'll talk more about it, but for now, this is the metric, which is kind of a summary metric which is not dependent on any threshold. It is dependent on the ranking of positive and negative labels. So here the if you have a concept of positive negative class and we'll talk about when it is useful and when it is not. But there are situations when uh, we cannot use ROC curves. A simple example is when we don't have a notion of well-defined negative class. For example, if you consider detecting objects in the images. So if the detector works by classifying patches, then the number of patches examined and hence the number of true negatives is the parameter of the algorithm, not the part of problem definition. Similarly, if you are doing information retrieval or in search system, whatever, usually we get to choose the initial set of candidate items, which are then ranked for relevance by specifying some cutoff, whatever, right? And then we'll partition this into positive and negative set and say that this set is relevant, this set is not relevant. But here, what we can notice is again that the size of the negative set depends on the total number of items retrieved, which is again an algorithm parameter and not the problem specification, right? So there are various situations when uh, first thing is there will be extreme class skew, which is prevalence will be extreme. For example, P by P plus N. This was my prevalence. And if that is, let's say, 0.01% or something, or even 1%, right? If prevalence is this extreme, ROC curves are actually not a good choice. And in those situations, precision recall curves might be better in terms of measuring model performance. Again, it's the same thing like ROC curve, but we are just choosing different metrics for X and Y axis. So again, you have model A and model B, model A and model B, and I want to compare these two models. So again, for each of the model, we will, for each sample and each model, we'll get a score between 0 and 1. We'll choose various thresholds starting from 0 ending up to 1 for each model, which will give me a list of precision and recall for different tau values. So for each model, I could get a precision recall curve. Again, here model A is better because area under the model A is higher, right? This is the area. So here model A is better, and this is precision recall curve. And we could summarize ROC curves as a single number also. Of course, we could see for various values of FPR what TPR can we achieve and things like that, and we can make a choice of a perfect threshold for our problem situation. We can do that obviously, but we could also have like a summary number. For example, area under the AUC, area under the curve is one choice. And of course, higher area under the curve scores are better. and maximum is 1. There's another summary metric for the ROC curve, which is called equal error rate, or it's also called crossover rate. And it is defined as a value which satisfies FPR is equals to FNR, and FNR is 1 minus TPR. And since FNR is 1 minus TPR, we can compute this equal error rate by just drawing a line from this corner to this corner. From here to here, we just draw a line, and the places where it intersects these two ROC curves are the ones which is called equal error rate. Okay, and here a lower equal error rate is better, obviously, because it's error, and minimum is obviously 0. So again, top left corner is the best in equal error rate also. So again, by equal error rate definition also, A is my better model. Okay, so let's now talk about class imbalance. And we have kind of touched on it, and class imbalance can be found by prevalence, which is P by P plus N, which is just the class Q definition, right? So there are many situations where class imbalance could be there, but especially in information retrieval, it will always be the case. The set of negative or irrelevant items will usually be much larger than the set of relevant items. And the thing about ROC curve is that it is unaffected by class imbalance, as TPR and FPR are fractions within the positives and negatives. So ROC curve is unaffected by class imbalance, and it might feel like, oh, it's such a nice property, but it's not. And the usefulness of ROC curve in these kind of situations is reduced because, let's say, if we focus on FPR, right? This is my FP divided by FP plus TN. Now, since the total negatives is much larger, okay, let's rewrite it in a different way. So I divide by FP throughout. So what I'll get is 1 by 1 plus Tn by Fp. Right? Now the thing is, because very large changes in absolute number of false positive doesn't really change my false positive rate. Anyways, the point is ROC curve is not affected by class imbalance, and it's actually a bad thing. And especially in these situations, precision recall curves can come to our rescue, which is another way to summarize your model performance, right? Okay. Now there are more ways to summarize PR curves. So one way to think about it is we can kind of quote a precision for a fixed recall level, such as precision of the first 10 entities recalled. And that is called precision at K, which means that if I retrieve K items, then out of those K items, what is my precision? The second one is called area under the PR curve, which we have discussed already. And yeah, I mean, these are two summary metrics for precision recall curve which you can use. And it's especially useful in retrieval setup or extreme skewed class population. Next topic is F scores and why we need F scores. We need F scores because it is possible to reach 100% recall. Because as you retrieve more and more documents, or as you move your threshold towards 1, we had this range 0 to 1 for probability, and threshold we could choose anywhere between 0 and 1. But if I choose my threshold to be 0, then everything is classified as positive class and my recall becomes 1, right? So 100% recall is achievable by choosing a certain threshold. But for this threshold equal to 0, my precision will be very low, maybe 1% or 5% or whatever, right? So in a way, that there's a trade-off between precision and recall. The highest recall system will not have the highest precision, and the highest precision system might not have the best recall. And I just showed you one example where it is possible to reach 100% recall, right? And because of that, we have to mix and match precision recall in a certain way so that we don't go into the extreme conditions or choose a bad metric. So one of the simplest form of metric is called F1 score. So I'll Okay, I'll clean it up a bit. So the simplest one is my F1 score, which is just the harmonic mean of precision and recall, which is basically just 2 by 1 by P plus 1 by R, or 2PR by P plus R. So that's my F1 score. Now the question might be like, why harmonic mean? Why not a normal mean or average? Just think about it. Average is P plus R by 2. Now, I just showed you how you can easily achieve a recall of 100, and precision you can maybe get like, let's say 5% or something. So it's very easy to say that this chosen metric can easily cross 50%, right? But uh, will it be a great system? Maybe not. And also there are some mathematical properties of harmonic mean. So in some sense, harmonic mean underestimates things. So let's take this situation. Let's say I recall all the entries so that all my predictions y hat n is equals to 1 for all n. Then my recall here in this case will be equal to 1. And exactly in this case, my precision will be equal to my prevalence, which in this case will be sum over I equal to yn equal to 1 divided by capital N. Now, if we suppose that prevalence is low, which is the probability of y equal to 1 to 10 to the power minus 4 or something, then my arithmetic mean will be p plus r by 2, which is 10 to the power minus 4 plus 1 by 2, which is almost equal to 50%. By contrast, if you try to find the harmonic mean for this, so harmonic mean will be what? Like 2pr by p plus r, which will be equal to 2 into 10 to the power minus 4 into 1 divided by 1 plus 10 to the power minus 4. And kind of this will come out to be around 0.02%. But in general, harmonic mean is more conservative. And in order to make this harmonic mean high, we need precision and recall both to be high. Then only harmonic mean will be high. But in case of this arithmetic mean, it can happen that we can increase this arithmetic mean even when one of them is very low. For example, in this example, right? So that's why this harmonic mean principle kind of help us. It's more conservative, but in order to increase the harmonic mean, we need to increase precision and recall simultaneously. Okay, so I'll clean this up a bit. So in this F1 score, what we have done is somehow we have weighted precision and recall kind of equally. So there's something called F alpha score, which is actually kind of a weighted form of this. So it is 1 by alpha times 1 by P plus 1 minus alpha times 1 by R. And here alpha is between 0 and 1. So here we can kind of adjust the weight alpha between 0 and 1 to give more importance to precision or recall or whatever, right? So that's my F alpha score. Now there's something called F beta score. I'll write down the formula first and then we'll see how it relates to F alpha. Although F alpha is more intuitive to understand, F beta is something which is more popular. So F beta is beta square plus 1 times PR divided by beta square P plus R. And here, beta square actually is between 0 and infinity. And there's also a relationship between F alpha and F beta, which is beta square is equals to 1 minus alpha by alpha. So anyways, like F1 score is actually equal to F beta equal to 1 score, or F alpha is equals to half score. This is my F1 score. And even in terms of F beta, if beta is less than 1, then we give more emphasis to precision. If beta is greater than 1, then we give more emphasis to recall. Okay. By the way, all this stuff which I'm discussing in this slide, you can also find it in Christopher Manning's NLP book. Uh, yeah. Now, a couple of more things about precision and recall is actually recall is a non-decreasing function in terms of number of documents retrieved. So if you retrieve more and more documents, your recall is guaranteed to go up. And usually in terms of precision, the more number of documents you retrieve, the precision can go down. Although it may not be like monotonic or something, but it will go down. And usually we are trying to find a trade-off and we use this F scores, F1 score or whatever. But the kind of a goal, and because we can choose whatever recall we want from 0 up to 100% or from 0 to 1, then the goal is kind of to increase the precision to achieve a certain recall. That's how you should look at it. So that's all about classification metrics. Next, we will look at regression metrics. It's not a lot, but still we'll look at few more metrics in the next video.